Hello, welcome to another further maths tutorial. Today we're introducing the topic of proof by induction. Specifically, we're going to be looking at using proof by induction to prove results involving matrices, but there are other traditional sort of problems that you need to prove using proof by induction that we'll be looking at in some future videos. But this video will also serve as the general overall introduction to proof by induction, looking at how that sort of method of proof works. So in order to do this, the first thing you need to know is what is that general structure. There are four main steps. The first one is quite a chilled step to do. It's called the basis case, and basically what you've got to do is show that the statement that you're trying to prove is true when n equals 1. So you simply got to plug in n equals 1 into the statement and show that it works. Step 2 is an assumption. You've got to make the assumption that the statement you're trying to prove works for a hypothetical value of k, where k is an integer. To establish this assumption, you write it down as part of your proof. Then step 3 is the induction step, or the inductive step. This is where you've got to algebraically show that if the statement is working for a particular value k, then algebraically it must also work for the step after, for n equals k plus 1, the integer after n equals k. The best analogy I can give for this is it works similar to sort of dominoes falling over. If you knock one domino over, it then knocks the next one over, and that then in turn knocks the domino after that over, and so on and so forth, and then it means all the dominoes eventually have been knocked down. The last step is the step that we always have to do for all proving questions, which is to do a conclusion. However, for proof by induction, there is a very particular conclusion you end up having to write, and within that wording, there's certain key points you need to make sure you're mentioning. So I will show you the wording that you need to write if you want to make sure you get the marks on these questions to make it a proper proof. Okay, but some of you might be wondering, why does this work? Why does this prove that something's true? Well, the first thing I'd like to point out, which is a quirk that some students end up thinking is a flaw that hasn't been spotted with proof by induction when they first come across it. It's well known that proof by induction is only proving something for positive integer values. Therefore, you should really only be using proof by induction for situations where that is what you're wanting to do it for. So you might notice for all the sort of situations we use proof by induction for, as standard questions in the exam, they're all things where they're things that will only work with integer values anyway. So that's why we only need to prove it works for integer values. So it's making sure we're using this type of proof when it's suitable to use this type of proof. And then the other aspect that students can't get their head around sometimes is, why does this prove something's true? Well, the best analogy I can give, I've already given the one about dominoes. The second analogy I can give is that it's a similar idea to how recurrence relations work for sequences. A reminder recurrence relation is basically a rule that tells you how to get from the current term in the sequence to the next term in the sequence. So let's say we have a very simple rule in sequences where we say next term in the sequence is equal to the current term plus 3. Now, a recurrence relation, a rule like this, is useless by itself. It only becomes useful once you have knowledge of one particular term in the sequence. Let's say the first term is equal to 5. Once you know what one of the terms is, then this rule, the recurrence relation, is helpful because it then tells you, well, if I got the current term as 5, the next term will be 5 plus 3, which is 8. And then, once I know that the second term is 8, I can then find the third term because the third term will be 8 plus 3 as well. So that will be 11. And then that snowballs from there to help you work out what all the terms of the sequence are. But as I said, it's only useful once you have the recurrence relation, but also a particular known term in the sequence. It's a similar idea with the induction step in proof by induction. The inductive step shows that if it works for n equals k, it must work for n equals k plus 1. By itself, that is a useless statement because, well, n equals k, k isn't something specific. But then as soon as you pair it with a known number you know it works for instance, you've proved that it works for n equals 1, then by combining this fact, the fact that it works with n equals 1, with the inductive step, you know immediately it must work for n equals 2. But then, by the inductive step, if it works for n equals 2, it must work for n equals 3. And then, if it works for n equals 3, it must, by the inductive step, work for n equals 4. And then, therefore, you can probably see that, again, we've had that snowballing effect where it must have worked for every single value, every single integer value after n equals 1. And so, therefore, you've proven it. Okay, so that's the general idea. Let's look at an example so you can actually see how this plays out. So our example is, we've got to prove that this matrix 1505 to the power of n will always be that matrix you can see in the right. Whatever the power you want to pick that's a positive integer value, pick that value, plug it into the formula, and that'll be the matrix instantly calculated for you. Worth pointing out that, again, the proof has acknowledged that it's only working for positive integer values, because that's what that bit I've just underlined means. Okay, so let's do the first step, which is the basis case. So all you've got to do is show that the statement we're trying to prove works for n equals 1. So to do that, well, plug in n equals 1 and see what you get. So first, plugging in n equals 1 to the stuff you have on the left-hand side, you'll have 1505 to the power of 1. And by the definition of power of 1 does nothing to anything. So therefore, it keeps it exactly the same. So that's what we get if we do the left-hand side to the power of 1. Cool. What happens if we do the right-hand side with n equals 1 plugged into that? Well, we'd get 1. We'd get 1/4, lots of 5 to the power of 1 plus 1 minus 5. We'll get 0, and we'll get 5 to the power of 1. If we then simplify that, of course, we've got the 1. We're going to have 5 squared, take away 5, which is 25, take away 5, which is 20, so we've got 1/4 of that. I mean, by the way, it's worth pointing out, if necessary, you could start showing ridiculous amounts of working for this. So if I'm doing that, this is what I could do. As I said, this is probably excessive. You could just do a little bit less than what I'm doing here, but it doesn't hurt. If in doubt, write stuff out for a proof. But you can see that, therefore, if I do follow this through, OMG, we do end up with exactly what we wanted. So we've proven that this statement is true for n equals 1. Now, some people like to do a conclusion, a mini conclusion, I should say, at this stage. They might go, therefore, true for n equals 1. And you're welcome to do that as well. If you do the conclusion particularly well, you don't always need to write this, but if in doubt, write this and do the full conclusion as well. If you want to guarantee you get the marks, it never hurts to do extra little details like that. Okay. Onto the assumption stage, which is very easy to do as well, actually, because all we've got to do is state our assumption. The assumption is assume that the statement that we've got written there works for n equals k. So therefore, assume 1505 to the power of k equals 1/4, lots of 5 to the power of k plus 1, take away 5, and then 0, 5 to the k. And that is the assumption done. We've stated what our assumption is. We're assuming this works. Cool. On to the inductive step. Okay, so what we've got to do for this is we now let n equals k plus 1. And so therefore we're starting on the left, and that would give us the left-hand side of the statement, 1505 to the power of k plus 1. What our goal is for the rest of the step is to just use algebra rewriting, algebra simplifying, to be able to rewrite this matrix that you can see and keep on rewriting it until we effectively end up eventually with what we see on the right-hand side of the statement, but with n equals k plus 1 plugged in instead of the n in there as well. Now, it's worth pointing out that does take a bit of effort sometimes, and so therefore this is, out of all the steps of proof by induction, the bit that will take up the majority of your time as part of these questions. And therefore also it's the hardest part as well, but it's not that bad, partly because something that a lot of students find helpful to do is to find already at the beginning what they're aiming for, by writing down a target, if you will. And to do that, all you're doing is effectively taking what you have on that right hand side of the statement and plugging in n equals k plus 1 into that. So therefore we have 1 quarter lots of, and it's n plus 1 in the power there, but therefore it's 5 to the power of k plus 1, which is k plus 2 in the power now. And then 0, and then 5 to the power of k plus 1 down there. Now, it's worth pointing out that you don't have to write this down, the target. You don't get marked for writing at the beginning what your target is. It's just something that some students find helpful to do so they can keep that in mind, keep themselves on track as they're going through it. And therefore it's reassuring when you start to see some of the things you see in this target start to appear in what you're doing. But the other thing I personally like to point out to my students is you sometimes might get away with it in marks sometimes, but I personally would say don't rely on, after you've written the target down, using that or assuming that because you've written it down, this is part of the proof itself. So if this needs, this matrix that we've written down will need to appear later on in the proof as part of the general structure of the proof. A good proof should be a nice linear journey taking you from what you started with to what you finish with, and it should all be mapped out step by step so the reader can see a nice path through the proof, if you will. Because we've written the target at the beginning, when it should be the thing that appears at the end, it's therefore good to assume that this isn't part of the actual proof, and just a little note we've written for ourselves to make our life easier, but isn't officially part of the proof. As I said, some of you might get away with that, but I would not personally, and I will write this same step later on as part of my actual proof. Cool. How are we going to do this though? Because the problem is, you see the matrix we've got, so written to the power of k plus 1 over here on the left, and the problem is that looks nothing like our target at the moment, and also it's kind of unclear how we're going to deal with that power, because dealing with powers and matrices is no nice way of doing that normally. So, there's nothing weird like you can't just apply that power to the individual things inside the matrix or anything like that. So this is where the assumption step comes in really useful, because what it means is we can use that result from the assumption step as part of our algebra rewriting. So for instance, that's going to be really helpful here because we've got a power of k plus 1. And the thing about a power of k plus 1 is because it's got a plus in the power, it can be split up using index laws. It can be split up as 1505 to the power of k times by 1505 to the power of 1. Which is then useful because now we've got the 1505 to the power of k, that's then what we can replace with the thing we wrote in our assumption stage. So therefore we can rewrite that as 1 quarter, 5 to the power of k plus 1 minus 5, 0, 5 to the power of k. Nice, still being multiplied by 1505. Good, good, good. That's nice because now that's dealt with the worst bit of it, the power. The power of 1 is just itself, and then the power of k has now been just already for us nicely replaced with a formula straight away. And all we've got to do now is multiply those two matrices together. So doing that, the first row in the first matrix times by the first column in the second matrix will get us 1 plus 0, so that's just 1. We'll get 1 times by 5, which is 5, plus 5 times a quarter, so that's 5 over 4, lots of 5 to the power of k plus 1 minus 5. Worth pointing out, this is a prove that question, so it is important you don't do too much in one step. making sure that every sort of step of the proof is shown as its own separate step, if you will. And then we've also got 5 lots of 5 to the power of k when multiplying the second row by the second column when multiplying the two matrices together. Sorry, I skipped talking about why I got that 0. That's me doing the second row in the first matrix times by the first column in the second matrix. Blimey, that's difficult to say. Okay, the rest of this is now just going to be us doing, tidying up the algebra inside that matrix to hopefully get what we can see in the target. So let's do that. We might choose to, for instance, multiply out the brackets in that top right hand corner element. So we're going to end up with 5 over 4, lots of 5 to the power of k plus 1. And then we're also going to have a minus 5 over 4 times by 5, which is minus 25 over 4. And then we've got the 0. And then conveniently, 5 times by 5 to the power of k is 5 to the power of k plus 1 by index laws. Which is great because you can see we've already got 3 out of the 4 elements in our matrix matching what they're meant to as shown in the target. So it's now just that top right hand element that we're needing to still work on. So 5 over 4 times by 5 to the power of k plus 1, dealing with that, well, 5 over 4 could be viewed as 1/4 times by 5, and therefore that 5 can now be combined with a 5 to the power of k plus 1 to get a 5 to the power of k plus 2, but therefore multiplied by 1/4. And then we also have 5 take away 25 over 4, and if you do that, you'll find that comes out as 5 over 4. Nice. We've also got the 0 and the 5 over k, 5 to the power of k plus 1, on the bottom row. Now, conveniently, we already see that we are getting somewhere. We've got the power of k plus 2 that we needed, but we also have a denominator of 4 appearing everywhere, which is important because we want the power of the factor of 1/4 out the front of that entire element. So that's what we're now going to do. We're now going to factorize 1/4 out of those two terms. So as I said, this does end up meaning I'm just rewriting what I got for the target, but the important thing is I'm writing it, now embedding it as part of the proof. It's one of the steps within the proof. But I'm actually not going to stop here. Again, you might get away with it that this is enough to show that, what we need to show is true, but I personally, to make it super mega obvious to the reader that we have got basically the statement with n equals k plus 1 plugged in, is to compartmentalize and separate out that k plus 1 in the place where the n was appearing in the original formula. So by that I mean, instead of having that power of k plus 2 left as a power of k plus 2, I'm going to rewrite it as a k plus 1 plus 1. And then on the bottom, well, we don't have to write that because that was just a power of n originally, so having k plus 1 there is what we're expecting. But that is now good because now what we've got is what we had on that original statement on the right hand side, but literally wherever you're seeing an n, we've now got a k plus 1 plugged into there. And hopefully, the steps are all set out in a nice, clear pattern. Admittedly, I've been working from left to right in a bit of a weird way, just trying to cram it all in one slide, but it's better if you just go down your page, of course. Okay then, that is the inductive step done. Now on to the conclusion, because the crucial thing is we have actually done enough to now prove the statement is true for all positive integers, because we're going back to that dominoes analogy. The inductive step by itself is useless, but combined with the basis case, it's now suddenly very important because we know it works for n equals 1. Therefore, we know by the inductive step it must work for n equals 2 because the inductive step shows that if it works for a particular integer, it must immediately work for the subsequent integer afterwards. But then if it works for n equals 2, by the inductive step, it must also work for n equals 3. And if it works for n equals 3, it must work for n equals 4, so on and so forth. So what we've got to do in our conclusion is effectively summarize or show our understanding of that. However, you don't have to go into as much detail as I was explaining in verbally to you just then. Here is the wording you need to write if you want to make sure you get the marks every single time for these proof by induction questions. So we have shown that if the statement is true for n equals k, then it must subsequently be true for n equals k plus 1. So that's explaining what the inductive step did by itself. But then combining that with the important bit, which is this only is helpful if we also know the basis case. So therefore we go, as we have also shown, it is true for n equals 1, by the process of mathematical induction, it must be true for all positive integers you can write, or you can write for n and then do the weird z with a plus to make it clear that it's positive integers. It's worth pointing out all those bits in the statement, in this conclusion, are important. The key parts are pointing out that if the statement is true for n equals k, then it's true for n equals 1. N equals k plus 1, sorry. So those are key, points you need to be putting across in your conclusion. Also pointing out that it's true for n equals 1, and that these things combined, process of mathematical induction is a nice posh way of saying that, and then pointing out it's true for all positive integers. So these are all the key facts that you have to mention as part of your conclusion along the way to get the marks for these questions. So there you go. All four of those stages combine to do what we know as proof by induction, and you must write all of those things down to get the marks. These things are worth actually an okay number of marks. They're not just like 1 or 2 mark questions, so you do get given the time to do these if they appear in an exam. Okay, hopefully you found today's video useful. In a future video, we'll be looking at doing proof by induction with some other standard problems. So do watch out for those videos as well. Goodbye.